Okay, let's take a look at the difference between velocity and acceleration. So velocity is how fast you're going. So it's how fast you're moving. Acceleration is how fast you're speeding up, slowing down, or turning. So how fast you're moving, how fast you're speeding up, slowing down, or turning. So let's take a look at an example to help drive this home. So let's say we're moving with a velocity of 5 meters per second. So every second we're moving 5 meters farther down the track or the road or whatever we're doing. Let's look at our acceleration. What if we have an acceleration of 5 meters per second per second? Again, it's meters per second per second. That means we're speeding up by 5 meters per second every second. Now let's look over here at velocity and say, well, let's monitor what happens during time. So we'll do a time, velocity, and distance table. And let's take a look at what happens. So we'll take a look at 0 time, 1 second, 2 seconds, 3 seconds, 4 seconds. And we'll look at what happens to the velocity and the distance during those times. So at 0 time, we're moving at 5 meters per second, but we haven't gone anywhere because it's still 0 time, so we're at 0 distance. Now, our velocity is constant here, so at 1 second, we're still moving at 5 meters per second. And our distance we've traveled now, after 1 second of moving that fast, is 5 meters. Now after the second 5 meters per second, we're still moving at constant speed. So we can just put those all the way down through here. Right? After the second, we've moved 10 meters. After the third second, we've moved 5 more meters for a total of 15 meters. After the fourth second, 5 more meters for a total of 20 meters. So every meter or every second, we've increased by 5 meters every second. So 5 meters per second. Now let's look at this one over here and say we have the same chart, time, velocity, distance, seconds, meters per second, and meters. And we'll look at the same 4-second time frame. So 0, 1, 2, 3, 4 seconds. Our velocity here starts off at 0 as well as our distance. We haven't gone anywhere yet. So our acceleration means that every second, right, we're going to increase by 5 meters per second every 1 second. So our velocity is 5 meters per second here. And because we're speeding up, a next second it's going to be 5 meters per second faster, so 10 meters per second, 15 meters per second, 20 meters per second. So we've been speeding up this entire time. Now to figure out what distance we've traveled, after 1 second, we went from 0 to 5, which is an average speed across this time of 2.5 meters per second. And if we did that for 1 second, then we've gone 2.5 meters. Now, how we get these distance numbers, you don't have to worry about that yet. We'll deal with this more later. I just wanted to show you the distances. Now, if we travel at 10 meters per second, so from 0 to 10 meters per second, the average speed during that 2 seconds was 5 meters per second. And if we go to an average speed of 5 for 2 seconds, we have traveled 10 meters here. And here, the average speed from 0 to 15 was 7.5. We did that for 3 seconds. 3 times 7.5 is 22.5 meters. We traveled that far. And down here, the average between 20 and 0, the average speed during this 4 seconds was actually 10 meters per second. And we did that for 4 seconds. And that ends up being 40 meters. Now, an important thing to note here. Notice how the distance, when it's constant velocity, is increasing by the same amount each time. Notice when there's acceleration, the distance changes by different amounts each time. And that's a key thing to have. Because we're speeding up, we're going to be traveling different distances in the same amount of time in that 1 second intervals. Hopefully that shows you that velocity is how fast you're moving. Acceleration is all about how fast you're speeding up. Notice velocities stay constant here, velocities increase here. The difference between velocity and acceleration. Okay, to drive home this idea that velocity and acceleration are really quite different, I want to show you an example of a low velocity object that has a really high acceleration. Because oftentimes we think if something has a big acceleration, then it must be going really fast. But remember, acceleration is not about how fast you're going, but rather how fast you're speeding up. So to do that, I've got this great high-speed video of a grasshopper. So let's watch it once through real quick to see what happens. Now, the nice thing about this video is down here at the bottom of the video, it gives you a time count of the time that's really going by in real life. And it shows you that this video camera is actually shooting 2,000 frames per second. So most video cameras shoot at 30 times or 30 frames pictures per second. This one's shooting at 2,000, which means it can slow things down to 67 times slower than they normally happen. So you can see the grasshopper starting to jump here, pushing off with the legs, pushing off, and then done jumping, and now just flies away. So we're going to try to calculate the acceleration of our good friend, the grasshopper. To do that, of course, we're going to need to know the change in velocity. We're going to need to know the change in time, how much time went by, and that's to help us find the acceleration. So the change in velocity, we're going to need an ending velocity minus a beginning velocity. We'll have to find those two numbers. And then for time, we're going to need a ending time minus a beginning time. So we'll have to find those two numbers. Now, obviously, our good friend the grasshopper is sitting still here. So his starting velocity is 0 meters per second. And we'll do our ending minus our starting to find our change in velocity. And then for our time, we need to find the starting time and ending time, and we can use our video for that. So what I'll do is I'll move the video forward until he just starts to jump. So you can see his little legs are getting ready, and right there, he just starts to push. So that's our starting time. 0.0445 seconds. Now you'll notice in the video that those are milliseconds, and that's why I put it into 0.0445 seconds. And that's our starting time. So we'll play again. We'll see when the grasshopper stops accelerating. See, he's pushing off right now, pushing off, pushing off, pushing off, and just left. So our ending time for the acceleration for his push is 0.0715 seconds. When we do that math, we end up with a change in time of 0.027 seconds. So now we have our change in time. You can see it doesn't take long for a grasshopper to push off of a log. Now we need to figure out our final velocity. So where does his speed end up at? And that we're going to do some estimation on. We know that velocity is equal to the change in distance divided by the change in time. Well, again, we can find the change in time in the video. We can use it again, but the change in distance is going to be a little tricky. So let's look at how we're going to do that. So we need a change in distance, we need a change in time, and we need to find our velocity. And this is our final velocity. So this is going to be our velocity right at this point. Once he stops accelerating, what velocity did he end up with? Now, I'm going to assume that the head of the grasshopper, about like this, is about half a centimeter long. So this is about a full centimeter. Now that's an estimate, but it's not a terrible estimate. So what we'll do is we'll track our good friend, the grasshopper, and see how long it takes the top of his head to travel 1 full centimeter. That'll give our change in distance would be 1 centimeter then, and our change in time will be how much time it takes. So let's write down we have to have a final time minus a starting time. And our starting time here is our 0.0715 seconds. And we'll find our ending time. So I'll play it forward until we get there. So that's when our grasshopper took till that time to get him over. So that's our final time. And we can come over here and say 0.0775 seconds. And that change in time, when we put it on our calculator, we find is 0.006 seconds. So our change in time is 0.006 seconds. And our change in distance was 1 centimeter, which is, of course, 0.01 meters. Now, if you're wondering if all these numbers are getting to you, don't worry. I'm just trying to show you a quick example of how to do it. You don't have to recreate this on your own at some time. So we know our velocity is change in distance divided by a change in time. So the grasshopper traveled 0.01 meters in 0.006 seconds. Put that into our calculator. And we get a speed for our grasshopper, our final velocity of 1.67 meters per second. 1.67 meters per second. So this is a fast walking pace. So our grasshopper doesn't really go that fast. So our change in velocity here, our final velocity is 1.67 meters per second for a final change, of course, of 1.67 meters per second. Now to find our acceleration, we simply take our change in velocity divided by time. So acceleration is change in velocity divided by a change in time. And we see that this is 1.67 meters per second over 0.027 seconds. Put that to our calculator. And we get the acceleration of 61.7 meters per second per second. We get this enormous acceleration for our good friend the grasshopper. Now this converts into something like 130 miles per hour per second. Now remember, our Tesla, our super fast sports car, was at 16.2 miles per hour per second, and this is grasshopper's 130 miles per hour per second. So it has a much bigger, six times bigger acceleration than a sports car does. Now the reason that grasshoppers don't go super fast is because they accelerate for a very short amount of time. So they don't have a lot of time to build up a lot of speed, but they do have huge accelerations during that short time. So hopefully we can see the real difference between velocity and acceleration.